cis-trans isomerism in alkenes. In alkenes, there is no restricted rotation about the carbon-carbon single bond, which means you can rotate about the carbon-carbon single bond many times and it's going to result in the different conformation. Sometimes in staggered conformation, some other times in the eclipsed conformation. Along with it, you can also get other different conformers depending upon the substituents which are present on this carbon. But in the case of alkenes, there is restricted rotation about the carbon-carbon double bond. Remember, the carbon-carbon double bond is made of one sigma bond and one pi bond. And this pi bond is going to exist as two lobes, one above the plane and the other one below the plane, preventing the molecule from rotation about the carbon-carbon bond. And because of this, the alkenes have the ability to exist as cis and trans isomers. If you have to rotate about the carbon-carbon double bond, then you have to break this pi bond. When you consider the structure of an alkene, each of these doubly bonded carbon is going to have 3 sp2 hybridized orbitals. And each of these 3 sp2 hybridized orbital is going to overlap with the orbitals of 3 other atoms to form 3 sigma bonds. Now, out of the 3 sigma bonds, one is part of the double bond. So remember, when you have a double bond, there is going to be one sigma bond and one pi bond. And the sigma bond is formed by the overlap of an sp2 hybridized orbital of one carbon with a sp2 hybridized orbital of another carbon. Whereas the pi bond is formed by the side-to-side overlap of the remaining p orbital that is present on each carbon. Now, because 3 points is going to determine a plane, each sp2 carbon and the 2 atoms that is connected to needs to lie in the same plane. In order to achieve the maximum orbital-orbital overlap, the 2 p orbitals need to be parallel to each other, and therefore all of these atoms, all of these highlighted atoms, all need to be in the same plane. We have concluded that alkenes have the ability to exist in cis and trans isomeric forms. Here is the structure for cis-3-hexene, and this is the structure for trans-3-hexene. Now, why this is called as cis-3-hexene? It is because the two bulky groups which are present on each one of these carbons are on the same side of the molecule. This is called as trans-3-hexene because the two bulky groups are in the opposite side of the molecule. So these two compounds have different configurations and therefore they can be separated. Now let's identify which one of these compounds is cis and which one is trans. For this, we are going to identify the carbons which have the double bond. So these are the carbons that we have the double bond. Okay. On this carbon, we are going to find out which one of these groups is going to have higher priority. Now the higher priority groups are the ones which is going to have higher atomic number. So between hydrogen and bromine, which one has got higher atomic number? Obviously, it is going to be Br. And similarly, we are going to see on this carbon, which one has got higher priority. We have chlorine atom here on the top and we have CH3 on the bottom. So between these two, which one has got higher priority? Obviously, it's going to be chlorine because this is the one that's going to have higher atomic number. And when you divide this alkene molecule into two halves, you can see that the two groups are on the same side of the molecule and therefore this is going to be cis. Whereas this compound on the right, where the two groups are on opposite side, is going to be trans. The easy system of nomenclature was devised for alkenes that do not have a hydrogen attached to the sp2 carbons. Now, in order to name the alkenes with the E and Z configuration, then we have to look into the relative priorities of the different groups that is attached to the sp2 carbons. If the two low priority groups are going to be on the same side of the molecule, then it is in Z configuration. Z stands for zusammen, which means together in German. And if the high priority groups are going to be on opposite sides, or in other words, the low priority groups are going to be on opposite sides, then it has to be designated by the symbol E. E means entgegen. In German, it is going to stand for opposite. In order to find the E and Z configuration of the compound, we have to apply a set of rules. The very first rule is to find the relative priorities of the different groups that is attached to the sp2 carbon. The relative priorities is going to depend on the atomic numbers. Higher the atomic number, higher would be the priority. In this compound, the two high priority groups are on the same side of the molecule, and therefore this is going to be Z. Whereas here, the two high priority groups are on the opposite side, and therefore this is going to be E. The second rule is that if the two atoms that is attached to an sp2 carbon are the same, then we have to consider the atomic numbers of the atoms that are attached to the tied atoms to determine the relative priority. So between these two compounds, let's find out which one is E and which one is Z. Let us take a look into the molecule on the left and identify whether it's E configuration or Z configuration. This is our sp2 carbon, and the very first atom that it is attached to, one of the substituents it's attached to, is a carbon. And even here, it is attached to the carbon. So there is a tie. So in which case, we are going to find out what are the atoms that this carbon is attached to. So this carbon is attached to two hydrogens, and it is also attached to one carbon. So the points of connection are H, H, and C. And on this side, this carbon is attached to two hydrogens and a Cl. So the different atoms are H, H, and Cl. Now between these two substitute, these two atoms, set of atoms, which one is going to have higher priority? Obviously, it would be this one because chlorine has got higher atomic number than that of carbon. So your high priority group is right here. Now on the next sp2 carbon, we are going to do exactly the same thing. The first atom is a tie, and therefore we have to look into the other atoms it's connected to. This carbon atom is connected to two carbons and an hydrogen. And on here, it is attached to two hydrogens and an oxygen. Now between these two, which one is going to have higher priority? Obviously, there is an oxygen present, which means that's the one that's going to have higher atomic number. Even though you have two carbons, you have one oxygen which is going to have higher atomic number than the carbon, and therefore this is the one that's going to have higher priority. And since the two high priority groups are on the same side, this molecule is Z. Here, the two substituents are on the opposite side, and therefore this should be E. The third rule is that if an atom is doubly bonded to another atom, the priority system is going to treat in such a way as if it were singly bonded to two of those atoms. And similarly, if an atom is triply bonded to another atom, the priority system is going to treat as if it were singly bonded to three of those atoms. Let's do some examples on these. This time we'll take the compound on the right and determine whether it's E or Z. Here is our first sp2 carbon. First, we are going to look into these two carbons right here and see what are the atoms it is connected to. So this carbon is connected to two hydrogens and a carbon. Similarly, this carbon is also attached to two hydrogens and a carbon. So that's kind of a tie, right? So HHC, and here again HHC. So you have to look into the other atoms it is connected to. So this carbon is connected to two hydrogens and an oxygen, right? And this carbon is connected to three carbons because you have a triple bond. Whenever you have a triple bond, you have to consider as if it's connected to three of the same atom. So let's write the atoms that it is connected to. So it's going to be H, H, O, but here in this case, it's going to be C, C, C. So between these two, which one has got higher priority? Obviously, it's going to be this one, since you have got at least one oxygen, which is going to have higher atomic number than the carbon. So this is our high priority group. Now let's look into the other side. The first atom is carbon here, and here also it is carbon. And let's look into the other three atoms that these carbons are connected to. This carbon is connected to two hydrogens and a carbon. So it's HHC. And this carbon is connected to an hydrogen, a carbon, and a carbon. Now between these two, which one has got higher priority? So you have hydrogen, hydrogen, carbon, but here it's hydrogen, carbon, carbon. So obviously it is going to be this one which has got higher priority because there are two carbons in here. So on the whole, this molecule here is E. And therefore, this is going to be Z since the two high priority groups are on the same side of the molecule. Let us do one more example. This is our sp2 carbon. Now between these two groups that are attached to it, Which one has got higher priority? Obviously, it is going to be deuterium. D stands for deuterium. Let's go on to the next sp2 carbon. The very first atom that it is attached to is carbon in both of these substituents. So that is a tie. So we have to look into the other atoms that it is attached to. This carbon is attached to two carbons and an hydrogen. So it's CCH. And this carbon is attached to an hydrogen. And since you have a double bond here, it has to be treated as two single bonds which is attached to the same atom. So this is also CCH. That's the second type. So you have to focus on the next carbon that it is attached to. We will focus on this carbon now. This carbon has got three hydrogens and same as this, right? So the three atoms that it is attached to are three hydrogens. And when you look into the next atom that it is attached to, so this is your next carbon. So this is attached to two hydrogens and a carbon. So it's going to be hydrogen, hydrogen, carbon. Now you can definitely tell that this is going to have higher priority. Since the two high priority groups are on the same side of the molecule, this is going to be Z. And this one is going to be E. Isomers for compounds with two double bonds. When you have two double bonds existing in a molecule, then you have to identify the configuration of the double bonds separately. So you have to first take this double bond, identify the configuration for it by finding the relative priorities of the different substituents attached on it. And you also again needed to take this double bond and find the configuration on this double bond. Let's first take this double bond and identify the configuration on this double bond. Since you have the two hydrogens on the same side, we can definitely tell that this is going to be Z configuration. This double bond is Z configuration. And here also it is going to be Z, since the two hydrogens are on the same side of the molecule. The two low priority groups are on the same side of the molecule. For this molecule, this double bond is in Z configuration. Since you have the hydrogens in the same direction, the low priority groups are in the same direction, or the high priority groups are in the same direction. But for this double bond, the two low priority groups are on the opposite side, and therefore this has to be E. Let's go on to the next molecule. This is our next molecule. This double bond right here has two hydrogens in the opposite direction, and therefore this is going to be E. Whereas these two hydrogens are on the same side of the molecule, and therefore this is going to be Z. Or here the two hydrogens are on the opposite side, therefore this is going to be E, and this is also going to be E for the same reason. Now we can go one step further and write the complete stereochemical name for these compounds. Okay, let's identify what is the IUPAC name for this compound first, and then we can add the configuration in front of it. So this is a diene, right? Because you have two double bonds. And let's find the longest carbon-carbon chain in this molecule. So the longest carbon-carbon chain is this, which has got a total of 1, 2, 3, 4, 5, 6, 7. Therefore, it should be heptadiene. Now we have to assign the numbers. From which direction are we going to go in? We need to make sure that the double bond gets the priority, which means it needs to get the lowest possible number. So if we have identified this to be our chain, we need to find out which direction we are going to go in. If we go from here to the other side of the molecule, that puts the double bond in the third position. But if you go in this direction, that puts the double bond in the second position. So obviously we have to number these carbons from here to the other side of the molecule. So the double bonds are now at 2. It's at carbon 2 and carbon 4. So this is going to be 2, 4 heptadiene. right? And leaving that, we are just left with the chlorine atom, and this chlorine is present on the first carbon, and therefore this is going to be on the whole 1 chloro 2,4 heptadiene. This is the name of the molecule without any stereochemistry involved in it, any E and Z configuration involved in it. And if you want to write the complete name of it, correct complete name of it, then we have to put the E and Z configuration of this compound in front of this name. So for which we are going to identify the double bonds, identify the carbons which has a double bond. So we have a double bond at carbon 2, and which is a Z configuration, so it's going to be 2Z. And the double bond at the fourth carbon is also Z, so it's going to be 4Z. And make sure to put this in parentheses. So this would be the complete name of this compound. And similarly, we can also find the name for these compounds. The only difference in these compounds is going to be the E and Z configuration. So just this part is going to be changed, right? So I'm going to put the names of these compounds here. And the only thing that we are going to change here is the things in the parentheses. Here in this case, it's going to be 2Z and 4E. But here it would be 2E and 4Z. But for this last compound, it's going to be 2E and 4E.